environment. So what this paper is aimed to do is we investigate and study the effects of as tiny as a metal obstruction object on the road to the signal strength propagation or to the radio wave propagation. So this is our objective, which is we demonstrate the low metal density impact of obstruction in comparison to obstacle-free environment. Then we characterize signal strength caused by metal blockage, and we will determine the best fit path loss models under bus and car obstruction. So the output or the contribution of this paper, the main contribution will be that it will assist researchers who are in the field of analyzing or developing and designing these propagation models based on V2I and V2V environment communication. So these are the main contribution. Before we could proceed to the designing and developing more accurate models, we will need to evaluate all the parameters that may assist in our future research. So the two areas that we choose for outdoor experiment, which is the freeway road for the free of obstacles and parking lot with car and bus obstruction at 2.4 GHz frequency band, and the presence of metal objects are in static. On your left hand, you can see the location. This can be considered as baseline because there seems to be no obstruction or metal object through the straight lane. And with bus obstruction, we require about 12 in a row, and the bus height is 3.0 meter, whereas its width is 10 meter. For car as metal objects, we also require at least 12 cars with the top height is 1.5 meter and width 4.4 meter. Okay, the hardware is ZigBee S2CRF modules. These modules we use for our experiment and research is because it's compatible with our short range data collection. Since in previous study, it has been proven in some literatures that at 2.4 GHz, these specific modules have been installed on real vehicles on the road, and the data has been transferred and communicated through the base station about 100 to 150 meter, a moving car with the speed of normal 50 to 60 km per hour, and it shows us no problem transmitting and receiving data. So this is the most suitable for our measurement and research. So that's why we will stick to the sensors instead of the latest sensors so on that we have, such as LoRaWAN and so on. And to configure the platform, we use XCTU for ZigBee, which is from DG. Okay, you can see how we set up our experimental. There's one here, the receiver, and at the other end is the vehicles. It will be at every point with the gap of 1 meter increment towards 50 meter. We will transfer at least 1 packet per second for at least 2 minutes at every point. Similar to the non-line of sight environment, where the object is substituted with a car and bus obstruction. So the car representing a smaller metal object, whereas the bus is a larger metal object. Both vehicles, these vehicles are used as a metal object as a reference because it is also has been proven in literature that metal object from cars and bus, it has been proven from the literature that its manufacture is made from cast iron and steel. For antenna height configuration of transmitter and receiver, we make it simple. We have three transmitter heights, different heights, 0.5, 1.5 and 3.0, which represent the handheld device, cars and car's height actually and bus. And for base station, it is fixed to 3.5 meter. Okay, these certain particular heights are actually in accordance to the validation standard parameters for predicting line of sight at 2.4 GHz. Based on previous literature for the standard parameters between 0.4 to 6 GHz, their standard height is between 0.5 to 3.5 meter maximum. Okay, with all this measurement data, we have obtained results to receive signal strength indicator. So by comparing all three graphs, we receive based on each antenna height of the transmitter. The transmitter 0.5, I forgot to mention just now, 0.5 is present the handheld device, whereas 1.5 is representing the car and 3.5 is representing the bus. So it shows that at lower antenna height 0.5 meter, the fluctuation is very obvious and severe, whereas for at 1.5 and 3.50 meter, it's quite mild. This is because at 0.5 meter, a low antenna height, it has ground effect reflection. The signal experience ground effect reflection. Before we have performed a experiment and channel measurement, we have conducted maximum Fresnel zone allowable test. So at least 1 meter. If there's obstruction under between 1 meter height, ground effect will take over. So that's why one of the reasons the signals fluctuated really severely on here. However, in the case of level attenuation level, all three graphs shows that and all three obstruction with bus obstruction shows a very significant drop after 18 meter. Yeah, so this shows that the signal that are caused by a larger metal object, have contributed to the diminution in signal strength. For path loss modeling, with that we model this result with path loss models for predicted models with to validate and determine best fit against measurement data. So all three shows that the log normal shadowing model fit the best for all trees. But for certain 1.5 meter antenna height in the middle, it has almost similar with the two ray, about 17.5 error, and almost similar with log normal and log distance. Okay, and in terms of signal level, for 0.5 meter and 1.5 meter, it has average of between -20 and -60, almost similar. And for higher antenna height at 3.5 times 3.0 meter, the RMSE level is much better. Under bus obstruction, again, log normal shadowing shows the best fit. However, for two-ray model, it does not follow at a certain distance for bus obstruction at 3.0 meter antenna height. For the signal strength level, it is quite similar and between -20 to -80 drop. And for higher antenna height, it has a much better value. Okay, what you can conclude from here is that the log normal shadowing is the best. However, two-ray model is actually quite consistent with car obstruction, but not with bus obstruction. Whereas triangle slope and log distance is not compatible with our measurement data, and so from this we have demonstrated the impact of metal object or based on low density vehicle obstruction, and we also compared to obstacle free, and the attenuation profile have been described and validated with the existing predicted path loss models.